All right, 7th graders, in your very last video of this school year, we're going to talk about inverse of a function. Now, you've heard the word inverse before, but what does that mean with what we're doing? Well, let's first go over what we're going to learn. We're going to find the inverses of functions. It's kind of like flipping them. Explore the inverses of functions. Find the inverses of functions algebraically, and then find the inverses of nonlinear functions. So let's start with our key idea. So our key idea is this. Recall that a relation pairs inputs with outputs. Now, a relation is like when you pair an input, which is your x value, and your output, which is your y value. An inverse relation switches the input and output values of the original relation. So basically, you're taking your x and you're taking your y and you're reversing them. That's all you're doing. So in our core concept, it says when a relation contains AB, the inverse relation contains BA. So in example 1, I'm actually going to put the answers and the work here. Example 1, find the inverse of each relation. All you do, here's your ordered pairs, -4, 7, -2, 4, and so on. All you do is switch the x and y around. So -4, 7 becomes 7, -4, which is called the inverse relation. If you had inputs like a t-table, your x and y values, you switch them around. But notice that the input is now 5. Like the input and output stay the same. But you just switch your values around. So now the inputs were all of the outputs, but now they're their inputs. So you switch the inputs and the outputs around. So exploring inverses of a function. Throughout this book, you have used given inputs to find corresponding outputs, such as y equals f of x for various type of functions. All it means is it's saying you've used equations and functions to plug x values in to get y values out. You have also given outputs to find the inputs. Now you are going to solve equations of the form y equals f of x for x to obtain a formula for finding the input given the output. So now instead of getting the y by itself, you're going to get the x by itself. So let's go to example 2. Here's how you're going to do this. You're going to let f of x equal 2x plus 1. We want to solve this for x. Then find the input when the output is -3. So what does this mean right here? Solve y equals f of x for x. That means what you're going to do is just plug in y. So I'm going to take the f of x out, plug in the y. So all I do is take y equals 2x plus 1. And now all you do is solve this equation for x. So you're going to subtract the 1 and then divide by 2. So x is going to equal y minus 1 divided by 2. You've now found the equation solved for x. You're now then going to plug in the output as -3. -3 goes into the y. This is really easy. So x would be -2. So we found the input. The input is -2 when the output is -3. All right, so now this is going to get difficult. Notice in example 2, the steps involved after substituting for x and y equals 2x plus 1, and after substituting for y and x equals y minus 1 divided by 2. So, step 1, multiply by 2, then you add 1. So we went opposite. Notice inverse operations in reverse order. Subtract 1, then divide by 2. So here, what's happening to the x? You multiply by 2, you add 1. Here, you subtract 1 and divide by 2. So you're subtracting 1 from y, and then you're dividing by 2. So why is that important? It's important because you should notice that these steps undo each other. These steps undo each other. Inverse functions are functions that undo each other. In example 2, you can use the equation solve for x to write the inverse of f by switching the roles of x and y. So notice what we did. The original function was f of x equals 2x plus 1. The inverse function is switching their roles. Notice this. This is like your y. G of x equals x minus 1 divided by 2. Notice what I did here. They reversed the x and y around. So, mathematical understanding. If you're getting kind of confused, this is a difficult concept to understand. So what do we know? I'm going to point this to right here. The term inverse does not refer to a new type of function. Rather, it describes any pair of functions that are inverses. This function right here is not a new type of function. It's relating itself to this one because they're inverses of each other. So, we're going to go even further. Because an inverse function interchanges the input and output values of the original function, the domain and range are also interchanged. So notice the original function was this. You'd have these t-tables, and you'd have the graph of f, which is this blue line. The inverse function switches everything around and becomes g. Notice the huge deal here. This is a big deal. This dotted line. Notice that the graph of the inverse function g is a reflection of the graph of the original function f. The line of reflection will always be y equals x, and you should have learned that last year in 6th grade. Y equals x, line of reflection. You should have done line of reflections before. That is always going to be true if you did the correct inverse function. So if you're confused, that's okay. But you should know that what we just went over was showing that a function and its inverse are related. So here's your steps to find the inverse functions. You're going to set y equal to f of x, so you're going to plug y in. You're then going to switch the x and y around, and then you're going to solve for y. Note that on the previous page, you solved the function for x, and you switch the roles of x and y to find the inverse function. You can also find the inverse function by switching the x and y first, and then solving for y. So let's do that with example 3. In example 3, if I can find it here, in example 3, you want to find the inverse of f of x equals 4x minus 9. Step 1, you're going to set y equal to f of x. So y equals 4x minus 9. Step 2, you switch the x and y around. X equals 4y minus 9. And now you just solve the equation for y. Pretty easy. You add 9, divide by 4. So y would equal x plus 9 divided by 4. Or you could have this. Y equals 1/4 x plus 9/4. Same thing. Easy. But those are your two equations. It's fairly easy. So, as review. Step 1, you replace the f of x with a y. Step 2, switch the x and y around. And step 3, you solve the equation for y. Now, if you actually did it correctly, here, we could have graphed them. If we graphed the f function, that's this, the red line, the g function, which is your new function. Remember, I can name it whatever I want. And actually, I probably should name it, instead of y equals, we should always put g of x, or you could do h of x or whatever, it doesn't matter, in for y. So if I did g of x, look at, does it look like they're reflected over the line y equals x? Yes. Therefore, these are inverse functions. Now, when finding the inverses of nonlinear functions, these would not be lines. The inverse of the linear function in example 3 is also a function. We know that from the vertical line test. The inverse of a function, however, is not always a function. The graph of f of x equals x squared is shown over here in blue. Here it is. Along with its reflection over the y equals x. Notice that the graph of the inverse does not pass the vertical line test. So the inverse is not a function. The inverse is not a function. When the domain of f of x equals x squared is restricted to only non-negative real numbers, the inverse of f is a function, as shown in the next example. So once again, if we have only non-negative real numbers, so here we go. Find the inverse of f of x equals x squared when x is greater than or equal to 0. Notice we have non-negative real numbers. Then graph the function and its inverse. So let's just graph it. But you would only have this. You'd only have the positive side of your parabola. So I'm just going to put the graph down. So let me find it here. Here we go. All right, so now that it's going to pop up, look at this. The blue is only the positive side. That's only when x is greater than or equal to 0. So you only graph when x is greater than or equal to 0. If I reflected that over the line of reflection, y equals x, you would get that. Now, if you don't know how to do that, what you'd do is this. You'd plug in values that are greater than or equal to 0 into x squared. Easy, piece of cake. And then you flip them around. So this would become x and g of x, and that give you 0, 0, 1, 1, 4, 2, and 9, 3. And that give you the red line. Now notice that is a function because it does pass the vertical line test. So that leads into the next thing. But you can use the graph of a function, f, to determine, the original one, to determine whether the inverse is a function by applying the horizontal line test. This should make sense. Because if you don't want to flip it, it's going to reverse. So you just do the horizontal line test to see if it works. So let's consider the function. Consider the function f of x equals this root of x plus 2. Determine whether the inverse of f is a function. Then find the inverse. So let's just first graph this. If you graph this, you would take your parent function and move it 2 to the left. So if we moved it 2 to the left, we would get this function, or this graph right here. Let's use the horizontal line test. Yes, it works. It does not pass more than once. So is the inverse a function? Yes, the inverse is a function. So now we need to find the inverse. So I replace the f of x with the y. I then switch the x and y around. I then just solve it. I square, that gives me y plus 2 equals x squared. Y plus, nope, let's redo that. That would give me y equals x squared minus 2. So y equals x squared minus 2. Now, this is huge. Majorly huge. Notice that this inverse is a parabola. My original function was not a parabola. So your inverse can't be a parabola. It cannot be a parabola. I'm going to say this again. You cannot have a parabola. So this is what we got to look at. Because the range of f, the original function, notice the range is all above 0. That means y has to be above 0. That means the inverse must be restricted to where x is greater than 0. So you're not going to draw this. You're not going to draw that. You're only going to draw when x is greater than 0. So you're going to get rid of all the non-negative. All the negative numbers. So it's just going to be that. So that's why in your graph it looks like this. If you checked it, here's your original graph. G is your new graph. Are they reflected across y equals x. Yes. So the inverse, you must say this. The inverse would be g of x equals x squared minus 2, but you then must put this, where x has to be greater than or equal to 0. The domain is x is greater than or equal to 0.